Echo Whiskey, Roger, join downwind left-hand runway 26, Quebec.
In determining just how an aeroplane flies, and the forces acting on it, its natural behavior and the ways in which we can control it, let us go to the grassroots of aviation, and from a considerable range take a typical light aeroplane as our example, the Cessna 150 Aerobat. It weighs 1,600 pounds fully loaded and is supported in flight by a wing spanning just over 32.5 feet. This wing, like every other, exerts a lifting force in level flight exactly equal to the weight of the aeroplane. To understand how an aeroplane flies, we need to know something about the air it flies in. What are its properties and how it behaves? This envelope of air that surrounds our planet has certain physical characteristics and patterns of behavior. Though it's invisible, it's made up of molecules like everything else. It has density and pressure, both greatest at sea level, where the pressure averages nearly 15 pounds per square inch. The further from sea level we climb, the lower the pressure becomes, until at 20,000 feet it's only about 7 pounds a square inch, and at 60,000 feet only about 1 pound a square inch. And as the pressure falls, so does the density and the temperature. But that 15 pounds a square inch at sea level is only an average. In fact, the pressure in any given place changes all the time. And as it changes, the air circulates around the areas of high and low pressure, and the wind blows. Now we realize that air is a fluid, seeking its own level like any other fluid. And we can feel the force of its moving molecules as they rush past us and pull at everything in their path. Moving air as a source of energy has been harnessed for centuries with ever-increasing skill and understanding. The aeroplane harnesses the same source of energy by the opposite process, by moving through the air. Let us look at the aeroplane for a moment. It's basically a simple and functional machine. Wings set at right angles to the direction of flight support a body or fuselage to carry the load. Smaller wings and a vertical fin at the tail end of the fuselage provide stability and control. In the nose, an engine and propeller provide the motive power. But it is the wings moving through the air that lift and support the aeroplane. How? To find out, we must first make air visible. We can do this in a smoke tunnel, having first turned it on its side so that we can relate it to horizontal motion. In the tunnel, we can put various solid bodies in the path of the smoke filaments, change their angle to the moving airflow, and see what happens. First, let's take a cylinder. Notice that the airflow curves closely around the frontal curve of its circumference, clinging to it, until suddenly it separates. It can't hold on any longer and becomes unstable and disturbed. It's moving too fast to tuck in behind the cylinder and maintain contact with it, so it has to let go. Now let's take a flat plate. Lying horizontally to the airstream, the flat plate disturbs it hardly at all. But turn the plate across the airflow and see what happens. Turn it back again, and we can see that even at the slightest angle to the horizontal, the airflow over the upper surface tends to break up. Next, a curved plate. This behaves rather better. The airflow is smoother, but it soon breaks away when the plate is rotated through an angle to the airflow. And at a smaller angle, the airflow breaks away underneath where the plate is concave. But if we look at the wing itself, we find that it's neither a flat plate nor a curved plate, but a combination of the two. It has thickness. The underside is almost flat. The leading edge is blunt and rounded, while the trailing edge is sharp. The upper surface is curved or cambered, and the wing is in fact attached to the fuselage at a slight angle to the horizontal. Cut a section through the wing, and it looks like this. If we set it in the smoke tunnel, we can see how smoothly the air flows around its contours. What's more, we can increase the angle to the airflow by quite a large amount without it breaking away. We call this variable angle to the airflow incidence, or angle of attack. But the really important thing is what happens to the airflow as it flows over and under the wing. Here is the airflow again, this time in slow motion and with an irregular smoke flow. Notice how the smoke accelerates as it moves over the upper surface of the wing, while the smoke flow below the wing tends to slow down. This is just what happens in flight, and it is this phenomenon that causes the wing to lift. For when a fluid in motion increases its velocity, its static pressure, which acts at right angles to the direction of flow, decreases. And when the velocity is reduced, its static pressure increases, so that its total sum of energy always remains the same. To prove it for ourselves, we need another kind of wing model. The surfaces of this one are perforated by a number of pinholes. Each pinhole is connected separately by an airtight tube to a manometer tube. Manometers measure pressure. When we drink through a straw, we suck in to reduce the pressure in the straw, and this causes the liquid to rise up inside it. If we alternately blow and suck on a manometer tube, the same thing happens. And so, if we put the wing section into a wind tunnel, any changes in pressure acting at right angles to the wing surface will be shown on the manometer tubes. Each tube is attached alternately to the upper and lower surfaces. Here is the wing section with wool tufts to show us the airflow. Now let's superimpose it on the manometers and see what happens. The manometers attached to the upper surface rise, indicating a considerable drop in pressure, while those attached to the lower surface fall, indicating a rise in pressure. And it's this difference between the pressures over the upper and lower surfaces that gives the wing its lift. In fact, the pressure pattern looks like this, with the pressure at any given point acting at right angles to the surface at that point. The pressure difference is greatest where the curvature is greatest, least where the surface flattens out. The resultant lift force acts through a point we call the center of pressure, and at right angles to the relative airflow. And so we have a cambered wing flying at a small angle to the horizontal, producing a resultant lift force exactly equal to the weight of the aeroplane in steady level flight. Lift increases with speed. We prove it every time we take off. It also increases with an increase in the angle of attack. let's follow that takeoff through in the wind tunnel. See how the lift builds up with the speed. In fact, it increases as the square of speed. Then as we increase the angle of attack at liftoff, there's a sudden, almost muscular increase in lift to help us off the ground. But the extent to which we can increase the angle of attack to the relative airflow is strictly limited. If we increase the angle by more than a certain amount, depending on the type of aeroplane, this happens. The airflow breaks up over the upper surface of the wing, the pressure pattern becomes unstable, lift decreases sharply. The wing has stalled. This can happen at any speed once the wing has reached the critical angle. Thus we can see that the pressure difference that gives us lift can only be maintained if the airflow over the wing remains smooth and undisturbed. The stall can be demonstrated in the air. The angle of attack is increased until it becomes critical. Lift is suddenly reduced. The aeroplane drops, pitching nose down, and quite a lot of height is lost before normal, controlled flight can be resumed. This can only happen when the relative airflow over the wing regains its normal angle and lift is restored. The stall can also occur in level flight. At normal flying speeds, the angle of the wing to the relative airflow can be maintained whether the aeroplane's in level flight, on a descending flight path, or climbing. Always provided that the speed is within normal limits. But if the speed's allowed to decrease in level flight, lift will also decrease. Then if we try to keep the aeroplane level, it'll begin to sink. When this happens, the relative airflow gradually changes. If the critical angle of attack is reached, the aeroplane will stall and will drop momentarily out of control. The speed at which the aeroplane stalls will depend on its weight and will increase with altitude as the air becomes less dense. Nevertheless, we must be able to fly slowly, and in particular to land slowly. To achieve this, we can change the characteristics of the wing by fitting trailing edge flaps. These flaps slide out from the wing and curve downwards as they do so. This increases the camber of the wing over part of its span. The upper surface of the wing now has even greater curvature, and the airflow therefore moves even faster, while the obstruction caused by the flap below the wing tends to divert more air over the upper surface, where the pressure is now even lower. In this way, more lift is gained without any increase in flying speed. With the flap fully deployed, lift is still maintained over the wing itself, but behind the flap, the airflow breaks up, slowing the aeroplane down by increasing another force acting on it, the force of drag. This enables us to approach the field at a steeper angle than we otherwise could, which gives the pilot a better view of the landing area, as well as a lower landing speed. Lift is the force that supports the weight of the aeroplane. Lift is generated by moving a precisely shaped and angled wing forwards through the air, causing pressure changes to take place around it. The force that moves the wing through the air is that of thrust. The force that resists its motion is that of drag.